Good morning, everybody. This is a session for one of our keynote speeches. Today, we are honored to have Professor Ray to give his talk on forecasting in the data-rich environment. Most of us know Professor Cai very, very well, and he's an academician of Academia Sinica, and he has also been the elected fellow of there are too many. American Statistical Association, the Institute of Mathematical Statistics, the Royal Statistical Society. In the past years, Professor Cai had helped the Institute of Economics in many different ways. And he helped conducting research projects, participating in all events, and bringing international faculties to the Institute, which help build econometric environment in academic Sinica, and in fact in Taiwan in general. So we are very happy that Professor Cai can give a keynote speech here. Please join me to welcome Professor Cai.
Thank you for the nice introduction, and thank you for coming to. Can you hear me in the back? Can I hear you? How about now? Is there, can I hear? Well, but that defeats the purpose. Anyway, that's fine. Thank you for the invitation. I'm glad to be here. I don't know how many times I give talk in this conference or in this workshop over the years. In that case, what I'm going to talk about is some type of forecasting methods in a data-rich environment. Okay, we are now, wherever you go, data science become a key issue. Every university you go, they all have data science programs. And one of the things is we have tons of data. And since the theme of this workshop is forecasting, so I'm thinking about when I summarize the forecasting methods available in a data-rich environment. So you can thinking about how to apply them in the future. The talk will be basically about application. There's some related research or some topics. I will remind you, but the talk basically will be, can you hear me now? Okay, will be about methodology. Okay, the outline like this, I will tell you what the problem is. It's the old problems, the statistical model I'm going to consider, and how to compare different methods. So that's out-of-sample predictions, and the criteria I'm going to use. Then the forecasting methods. There are many forecasting methods available in the data-rich environment. I'll mention some of that. Then show you some empirical examples and summarize the empirical result. And then we open for discussions and so on. So the problem is like this. Suppose I'm interested in a variable yt, and I have tons of predictor variables. I use a capital XT, means the collection of all the predictor available. At the forecast origin, t equal to n, I'm interested in ym plus h. This h is the forecast horizon. So you can think in this way. What I like to do is really interested in the conditional probability distribution of y t plus h given xt. And often in real application, we maybe focus on the point forecast. So just interested in expectation of y t plus h given xt. Under what condition can be classified like a data-rich environment? The kb is the dimension of xt. X may contain variables of different frequencies. For example, the nowcasting become popular. You can have your interest in forecasting quarterly GDP. You can use monthly information, daily information, weekly information, so you can expand the dimension to a certain degree. The sample size, the forecast origin n, may not be necessarily greater than the number of variables. So we have penalized method like lasso regression or some other method. You penalize partial least square type of methods. You can do that. So the available data will be xt from t from 1 to capital T. Capital T will be greater than n because I will split the data into two pieces. One part for estimation, the other part for the out-of-sample predictions. In theory, we call that data-rich environment. In some sense, it's both n and k goes to infinity. So that's a statistical inference or econometric inference. That's classified like a data-rich environment. Of course, in real application, both k and n are finite. There are some basic model I'm going to use. When you compare different forecast methods, we like to have some statistical method we employ. The first one is the pure time series models. I use write down this AMA model, autoregressive movement average type of model. It's including seasonal model or any type of thing is allowed. I just like this a simple time series model. So the first category is a pure time series model. All the time series model you can be classified into this category. The other one is time series regression. So we have some exogenous variable xt. Xt can include some lag value as well, but ut will be a time series process. So that's a time series model with regression, error, and so on. That's another class of model I'm going to use. The tree, the regression tree, because we are in a data-rich environment, I briefly mentioned what the regression tree look like and how to use that. I use a binary tree. People use also the like Lowe's tree and some other tree, but binary tree is the most simple one people like to use. Like I mentioned, we allow for number of variables to be large, so we have to regularize different also the regularization type of methods you can use. I will use the auto-probing model. That's for comparison. You like to do compare the deep learning and so on. So it's a categorical type of variable. What you have, the auto-probing model is a simple model. Suppose what you observe is a categorical variable. So yt here is the category J. If you have the yt star is the underlying variable will be a continuous variable. That yt is a categorical variable. So it's called the auto-probing model, and assume they are C category. And you can use this type of model to model a lot of things. I mentioned some of that in the financial applications. You can also partially square principal component regression related to the diffusion index of Stark and Watson and so on. Those are all related issues. Now, for the out-of-sample forecast, that's basically the method I'm going to use is to divide the data into modeling and forecasting subsamples. So the forecast origin is little n. So from 1 to n, I'll do the modeling, and from n plus 1 to capital T is for forecasting. Okay. In this talk, I will focus on one step ahead predictions, but in theory, you can extend to more than one step. I use 3 criteria to compare different methods. One is bias in the prediction. The other one is the mean square error of the forecast. The other one, the mean absolute error. Just in case you like the robust type of measure, you'd like to do that. I didn't do the density comparison, but those are possible. Just a little bit more complicated. You can do that. The forecasting methods I'm going to discuss is called the benchmark, or the simple model. That's the most commonly used method people are going to use. Maybe a random walk, or a constant, or a pure autoregressive model. Pure AR model without any exponential variable that's served like a baseline model. I use a back testing. Basically, it just, we'll talk about that in a second. Some model averaging, you assume that maybe the time series you have is subject to structural change. You like to use some simple method to do model averaging, can reduce the variability. The diffusion index, those are the Stark and Watson type of method, partial least square, can also be used. Random first, or some modification. I mentioned what type of modification we need. And then the lasso or elastic length, the type of penalized type of method. Those are in blue are the packages available. You can implement the method I'm talking about. Then the deep learning, that basically is a multi-level network. So that we'll talk about, and that's the forecasting method I'm going to use in this talk. Benchmark, random walk with drift, that's the most commonly used one, because sometimes it's hard to beat the random walk methods. Stationary time series, I may use just a constant, just use the mean of the forecasting sample, mean of the modeling sample to produce forecast. With a simple AL model, the order can be selected by information criteria. That's the method we're going to use. Now let me tell you what back testing is. It's some sort of terminology people use in finance, but in statistics, it's just out of sample prediction. You start with forecast origin, and in the modeling sample, you can select a model, a time series model or regression model. Those can be done by automatic methods. In the past, I'm sometimes against doing automatic model selection, but now in the data-rich environment, we have to do that. There's no way you can analyze. One of the examples I'm using with one of my friend and Joe's friend to, like Daniel Pena, we try to analyze. We have more than about 3 million time series. And it's impossible to identify model one by one. You have to use some automatic method to do that. Those are about the expenditure a household spend on the supermarket every week. They spend a certain amount of money and have about 3 million customers. So that's the time series we like to analyze. So automatic method we're going to be used. You can identify them. Once you identify the model, you estimate the model. For every forecast origin, t from n to t minus 1, you estimate the model, and you predict the next step, and you do estimate model and predict the model. If necessary, you can also identify the model. Those can be done automatically. So the key in here is you do fit the model. Once the new data available, you do fit the model. That's a back testing. Simple way to do the model averaging is like this. This is a very simple way to do that. What I'm going to do, you worry about stationarity of the time series you have or the process you like to do predictions. Now suppose I give M model. M is just a number model you can use. You can pick any one you like. Then I divide the block. Okay, the block size G is just n divided by m, because I have n original observation for modeling. So the block size will be Z. So first block, I use all the data to find a model. The second model, I drop the first Z observations. Then I drop the second 2 Z observations and so on. So later on, only use a small group to do that. And then take a simple average. Simple average is a very simple way to reduce the variability. Why this? Because we worry about non-stationarity. A formal procedure would be like this. We are at the forecast origin n. Then I look backward. I can test for the structural change. Once I have a structural change, I put that point like a breaking point. Then I do test the model for structural change. That's a backward type of testing. But that to me it becomes complicated. So I just divide them into blocks. But the simple idea allows you to do that. Okay? The penalized type of method, in the estimation part, you like to estimate your coefficient beta here. Remember, X is high dimension. Now, if the sample size n is less than the dimension, you cannot estimate that. So we have put a penalty there. Because the elastic net is a linear combination between L2 penalty and L1 penalty. So the L1 penalty is just a lasso type of penalty. The L2 penalty is a least regression. And people turns out some combination of them is easier to do, perform better in many situations. Typically, how do you select the penalty? You use cross-validation to select what type of penalty is good or what type of alpha is needed, because there are penalty involved. The alpha can be selected by cross-validation, but in a time series setup, the cross-validation is not that obvious. So that's the one reason we like to worry about that. Also, the lasso type of method can fail if you have a strong serial correlation. I think I talked about that a couple of years ago. So, but in any case, those can be solved. You just use some other method. People also propose called the partial least square, called the orthogonal greedy method to select the model, but those can be classified in this category. The regression tree is rather simple. Basically, the procedure like that. You select one of the variables from the predictors. You select ith variable, but minimize this criteria, and also select threshold. There's a branch. You can divide that into two pieces. You like to minimize that. Here, YIR, Y1 bar and Y2 bar are just a mean of each part of the data corrections. Okay. So that way, by first one, you start with select one variable, divide the data into two pieces. That corresponding to your tree, you grow into two branches. For each branch, you repeat the same thing. You select one variable to do split. Once you split, you minimize the variability. And that is called the tree type of stuff. For example, now the PM 2.5 seems to be a hot topic. Everyone talk about that. Those are PM 2.5 for Shanghai. Okay. Those are from the U.S. Embassy in Shanghai. You can see that. I apply a simple tree to do that. So this will be a tree structure. For if you're interested in predicting the Shanghai PM 2.5, okay. The L1 means leg 1. This is a daily stuff. So if leg 1, for example, if you yesterday thinking about today's PM 2.5, if yesterday PM 2.5 is less than or 53.5, then you go to the first branch. If yesterday is greater than that, you go to the second branch. And within this branch also, if yesterday is less than 34, then you go to this tiny branch. Otherwise, greater than that, you go to second branch, and so on. And this lag 367, because of daily observation, we have annual cycle, so the lag involved is more than 365. So that's a 367 day before, and you can do that to do classification. So these are tree structures. In terms of prediction, those are the average for all the observation within this category. And you just use this number to do predictions. So it's a very simple structure, and you don't have to do something. You just continue to do partition. Of course, you have to worry about the tree. You can think about if I m data point, at the end, if you continue to do that, at the end you have n leaves. That's too complicated, overfitting. So you have to prune them. You have to put some penalty, and you can tree not too complicated. So that's basically the thing I have here is stay here. It does a way to do a tree type of forecasting. So that's a tree structure. To do prediction, use the regression tree. You can do the classification for that as well. Okay. Now, what about random forest? And I also put a modification. The modification is just to take care of the time series content and so on. What is random forest? Look in this way. If you just use a tree like the one I mentioned here, it's only one tree, and because you divide into category, and use the mean to do the prediction, and this is only finite number. It's not very precise. But random forest is like this. You use many, many trees. You can use 1,000 trees, 5,000 trees. You can use many, many trees. But if you use the same method to do that, you grow the same tree. That's not useful. So what the random forest try to do is to obtain as many different models as possible. Even though originally I have k variables to grow tree at every split every split, I only select m variable for the splitting. So even though I have k variables, but to grow the random forest, I only select m. M is much less than k. Okay, so I select randomly m variable to do the splitting. Because every split, I select m variable for the splitting, so the tree I grow will be different. So that's the way you achieve the model averaging type of stuff. In random selection, in the sense is, I like to cover as many possible things because the variable, if you keep selecting the same variable, then you are not informative. So that's called the random forest. And this simple idea turned out to be quite useful. This idea seems to be quite useful. We'll see that in a second. Since we are in a time series content, then we understand my modification is rather simple. I have k variables, but in the time series analysis, certain legs are more important than others. For example, talking about PM 2.5. Yesterday, PM 2.5 will be more important 10 days ago. Okay, so why do I have to randomly select m variable for splitting? So the idea is rather simple. I divide the variable into two categories. One category, category 1, very small, contain a very small selected variable. Those variables will always be used in the data splitting. The rest of them, a large many variables, they can be selected randomly. So that's a very simple type of modification. It turns out to be useful because of the time series nature of the problem. So that's the modification. Now talk about deep learning. For those who understand neural network, we do have the expert here. He did a lot of neural network many, many years ago, and probably thinking in this way. This just people call this one a 3 by 4 by 2 type of network. I have X represents the input, H represents the hidden layer, and Y represents the output. So what I like to do, this network like this is a 3 input, and I have 1 layer of the hidden layer is only 1, and that had a 4 node in this case. I have 2 output. And the connection here is called the feed-forward type of network. Okay. In reality, you can have feedback, you can have a very complex structure, but in the implementation, to do that, we simplify that. And this one, the structure like this, the feed-forward type of network, in the machine learning, they call this type of structure, it restricted to Boltzmann machine. That's the terminology they use. They only feed forward. Okay, there's no connection between H1 and H2, no connection between H2 and H3. It's always a fitting forward. Those are for simplification and estimation. Because in the multi-layer type of deep learning, you use many hidden layers. If you do this type of forward restricted Boltzmann machine, you can train the network 1 layer at a time. So it simplifies the calculation. So that's the reason people use this type of structure. We call the architect of the network and so on. The information process, the arrow means that the information from X1 to H1, X1 to H2, and so on. How do you process the information? They're called activating functions. Activating function, typically, you can either do this regression or the arctan type of methods. There are many methods available. Typically, we call the activating function is a logistic type of regression, allow you to process that. Okay, so that's a network structure. Deep learning is just like this type of network, but there are many, many nodes. Here I only use 3 input. You can have thousands of input. The hidden layer, you can have 1,000 of nodes, and you can have a multiple of them, not only just one. You have multiple of them. Okay. The output can be scalar, can be multivariate. You can all sorts of possibilities. So that's called the deep learning type of structure. Now, deep learning different compared with the traditional network type of structure because you have a very high dimension. The model is complicated, so you have to put some restriction on the way you can estimate your model. And one of them they introduced called the long-short long short type of memory tend to overcome what the difficulty in estimation. You think about logistic regression, and to estimate the parameter, typically people use a gradient method to do the estimation. Okay, the gradient method, the one you do, you can use a gradient so you can decide which direction to go and how much to go and so on. If you're thinking about logistic regression, you take a derivative of that. Your derivative will be less than 1, between 0 and 1 most of the time. If you multiply a lot of number, you either keep chain rule because the high level type of, you keep doing chain rule to do the calculate the gradient, then the gradient will become close to 0 quickly, and that's no good. So they introduce some way, they call the short-term, short-long type of memory stuff. You randomly drop some of the gradient instead, and then you can train them in some, there's some way to do that. So those are, for you interested in the deep learning, that's one thing you can do to do that. Okay, at this moment, I use these 2 packages in all, but they only can handle the categorical variable. They cannot handle the continuous variable. But in our application, in some sense, not too bad. If I divide, like, say, 20 categories, 30 categories, you can obtain a reasonable approximation. You still can train that. To demonstrate that, I will show you, that's the last regression. Another thing I'd like to mention before I show the example. Because it's a logistic regression, so in some sense, it's a categorical or generalized linear model. It's a generalized linear type of model. And since the time series with generalized linear model, and we need to do some research to justify the method available. For example, the consistency of the Lasso type of estimation for the generalized linear models. The original one for the RID observation was proposed in 2005. Now we are working on, if you have a time series dependent data, how do you run this type of generalized linear model, Lasso type of regression? So that related theoretical issue, I'm not going to talk about that. So to illustrate about deep learning, this is a modeling financial application, the transaction by transaction price change for the Walgreens. Walgreens is a convenience store in the US. You can find that many places. In any case, I look at one day, that's February 6th of this year. And in this year, there are about 29,000 price change, because that's a trade. Every day, Walgreens had about 30,000 transactions. Okay. Those are only for the normal trading hour I'm working on. So we have about 29,000 price change, and price change in the continuous variable, theoretically speaking, will be a continuous variable. But if I show you the histogram of price change, about 29,000, about here. So basically, it's about 71% of them are 0, and another maybe 13% are increased by 1 cent, another about 13% drop 1 cent. Then about maybe 2% increase about 2 cents, and drop about another 2%. A little bit symmetry, but not quite precise. It's very rare to have a high values. So those are, even though the range seems to be big, but they are very small. So follow the tradition to simplify that. People will just code the price change into categories. So here, what I did is, based on that, I divided into 7 categories. The consecutive price change is dropped by 2 cents or more, between 1 cent and 2 cents, between 1 cent and 0. 0 itself is 1 category, and so on. So I have 7 categories. So that's the way people use. There are some additional variables, the duration between the transaction that reflect the trading intensity. Okay, that's important. So time, TI, is the ice trade. The time of the ice trade comes from the midnight. So TI, T sub I minus T sub I minus 1, that's the duration between 2 consecutive trades. The other time, this duration is 0, because 1 second you can have multiple trades. But luckily, now they measure the time in the seconds, in a millisecond, not 1 second. 1 second is too long. So now measure in millisecond, so that's a DI. You also, SI is the volume divided by 100, because the volume is one way to reflect the volatilities. So you have trading intensity, you have volatility proxy for the volatility. So those are the variables. And the category defined in this way, 7 categories. I have 6 variables. So the regressor I use, the experimental variable I use a 3 consecutive 1. Okay. So this has 6 categories, and I have D and the duration and the volume. That's the one people use. So the state of the art by Hausman, Andrew Lowe, and Craig McKinney, they proposed called the Olo-Povey model to model this type of price change. Okay, so that's a price change. The original one is original price change divided into category in this way. I only plot 1,000 observations. So the model used in comparison, in this one I have 29,000. I reserve the last 2,000 for forecast out sample predictions. The in sample, about 27,000, 71.3% consecutive trade without price change. So that would be the baseline model. My baseline model is I always predict no price change. So based on the sample, 71% to be correct. Okay. So that's the most simple baseline model. And I compare that with the Olo-Povey model and the deep learning type of model. So this is the Olo-Povey model in the forecasting sample. It turns out Olo-Povey model always predicts the no price change. Okay, I use that and to do prediction in the forecasting sample. Olo-Povey model always predict category 4. Category 4 is no price change. And this is the observations. In this period, the correct prediction of the Olo-Povey model is 71.9%. It's slightly different from the baseline model. If I use a deep learning, I use 27 and 10 and 1. That means 10 hidden node and so on. So the correcting successful prediction jump to about 72.5%. So increase about 1%. You can think about 1% improvement, not big, but in finance, this is important. Okay, in finance, this is a substantial improvement. I was impressed, especially by this one. The prediction is dropped by more than 2 cents consecutive trade. This actually, the observed, and this one actually picks that up. That in some sense, deep learning, it has some particular power in that sense. So that gives you some idea about what the deep learning try to do. Any questions? Okay. Now, the empirical time series I'm going to use for the model comparison already mentioned many methods and so on. Look at the CPI. This is all opens and all items like CPI. The data set is from 97, that's the monthly observation, to September of this year. Okay. And I also look at the monthly industrial productions from January of 60 to about July of this year. Those are the second time series is the one used by Stark and Watson, and they have also another 121 macroeconomic variables. So you have about 122 variables together. Then I use Taiwan's PM 2.5. There's one monitoring station near the Kaohsiung city. Okay. In Taiwan, we have about 71 monitoring stations for PM 2.5. They actually keep very good record. The hourly PM 2.5 started in 2006. They have hourly PM 2.5, PM 10, the wind direction, wind speed, and relative humidity, and some other variables. They have a good data set, about 71 of them. So in reality, you can analyze a 71 time series because most of the monitoring stations on the west coast. In the Pingdong and the Hualien, each place only one monitoring station. But most of them in the west here. You can actually doing that Okay. So I'm looking at one station and to tell you how to do the prediction of PM 2.5. Okay. I aggregate daily to hourly observation to daily, but I also use the first 6 hours observation. So what I mean is, at morning at 6 o'clock when you wake up, you can update your predictions. If you only use daily observation to predict today, yesterday you can predict today. But use a mixed frequency at the morning, 6 o'clock this morning, I can update my prediction of the day. That's one thing we call the mixed frequency type of predictions. I also do hourly observations, but use a daily maxima. Use a daily maxima because the daily average of 24 hours and use 6 observation. You say, well, you already had about 25% of the data available. So that may not be that impressive. So what I did, I used the daily maxima because the maxima is the one we care most. So I like to, for every day, I look at daily maxima. I predict the daily maxima for tomorrow. But tomorrow morning at 6 o'clock, I can revise my predictions. Because after 6, your activity, typically most activities up to 6 o'clock in the morning. So in 6 o'clock, you can update your prediction. So that's the general idea I use there. Because the 10 years observation, hourly, so that's the observation. For those who are interested in the time series with mixed frequency type of stuff, PM 2.5 is a very interesting thing to study. The data set is quite complete. And this is every year you have so many observations. It turns out, the reason I mentioned that, because if you're really interested in this one, in the time series analysis, typically people use a structural model. You have a seasonal part, irregular part, the trend part. And like George did a lot of things in the seasonal adjustment and so on. For this one, because it's 10 years of data, every year you have 7,060 hours. So the period, annual cycle, the period is 8760. And you try to put this type of method into any time series package, you cannot estimate. Okay. Doesn't matter how you do that. You just cannot estimate the seasonal time series model with period 8,760 observations. Okay. I tried that and come to find out my computer said you don't have enough space. Okay. And I have 71 of them. 71 monitoring stations and many, many variables. So it's impossible. You have to do something about that. So that's an interesting thing. More than that, because the seasonality, the period is 8760, it transfer into the frequency is about 4.2 times 10 to the minus 4. It's so close to the zero frequency. Even with 10 years data, I cannot separate my trend with the seasonality. Okay. I was trying to do structural estimation, structural model. So I estimate that, wanted to get the program to work. Then I try to plot the seasonal, the trend part. My trend part is capture the seasonality. I spend a lot of time to think, well, why is that the case? Did I make a mistake in my program? At the end, my program is correct. The reason is, even with 10 years, I don't have enough data to separate the trend frequency at zero with the seasonal frequency is a 4 point something 10 to the minus 4. We cannot separate. That means in the spectrum, the two peaks is so close to together, doesn't matter how we smooth them. You cannot separate them. Then we have to be very tiny to separate. In any case, that's a related issue. But if you're interested in that, the data are available. The good thing about Taiwan is they keep the good record of all the data is available. You can do that. And anyway, go back, this is a CPI example. That's the inflation. Okay. Monthly inflation, I like to do prediction. There's an interesting time series in the sense is you understand that not a stationary time series. Because here in the past, you sometimes only assume discrete values, okay, not continuous variables. Later part is nice, but the beginning part is not that nice. So what I did is the study plan for this one is like the monthly inflation. I use 24 lag. That's for simplicity. That's based on the AIC criteria. I select A or 24. And I reserve the last 40 observations for predictions. And for each models, for each type of method or model, I use a 1 and then try to do that. And for the benchmark, in this case, I just use a constant because the inflation is a constant. So that's the result of the different method to compare that. The benchmark, you just use a constant. Okay, the sample mean of the modeling period. Of course, the sample mean change and as the forecast origin change. The back testing, I let the model automatically identify a time series model without anything else and do the prediction. The non-stable forecast is I use a method, I divide the data into 15 pieces. One uses all the 15 pieces to do estimation. One uses 14 pieces, one uses 13 pieces, and do all. And then take the average without any testing type of stuff. The unstable, I also try 10 model instead of the 15 model. The PLS means the partially square, and the PCR means the diffusing index, principal component regression. This is the last type of regression. The alpha equal 0.9. That's the best alpha can be available. Random forest, use a 1,000 tree. The deep learning, I use a 15 category. Because remember, deep learning only applies to categorical variable. I divide the information into 15 categories. And in this case, the deep learning, I have 24 variable. I have a hidden layer, 1, 2, 3, 4 hidden layers. The first layer is 15 nodes, and the 5, 5, 5, and so on. So that's the result you can see. Okay. In some sense, all the modern type of method are improved over the benchmark. That's not too surprising, okay, because that's what we have. Okay. But on the other hand, some of the method, like a backtest, that's a pure time series model, seem to be reasonably well. The model averaging for the unstable model is also reasonable. Okay. So that's, yeah. Oh, those are all quick. This is all very quick. You don't have, I use even my Microsoft Surface can do the calculation. Okay. It's only when you have tons of data, like a PM 2.5, that type of stuff, you don't into problems. The rest of them are not easy. Oh. I didn't actually compare the time because when I submit the job, the output come out. So I don't really worry too much about the time. But of course, it's probably a good way to compare the time too. Okay. Okay. The second one is the industrial productions. Okay. I think I use the last 120 observation for the forecasting comparison. Now this is used by Stark and Watson. So total input variable is 610. Okay, so because I have 122 variables and I use 5 lags. Okay, so total is 610, and you can the last 120 for the forecasting, rest them for modeling. Okay, again the benchmark I use a constant to do that. So here's the result. Here's the result. And you can see that the back test in this case, in the non-stable model, in this case, actually, is impressive in the sense is only use its own past. Do not using any other 121 macroeconomic variables. It's only use its own past to do predictions. So that's the result you have. Okay. Again, here deep learning I divide into 20 categories. The random forest and the random forest we select. The select one improve over the one. The only difference is select I use because I use lag 5. For every selection, the industrial production variable 5 lag is always included in the selection. I divide the variable into 2 categories. So the first category always involved in the splitting, the candidate for splitting. The rest 605 of them in random selections. So that's what we have. And you can see that random forest is a very simple thing and actually doing quite reasonably well. So even the tree is a very simple structure, but they actually doing quite well in that sense. Okay? The principal compound regression diffusion index, in this case, to obtain reasonable result, you have to get to 75 components. Okay? Partial least square is 17. So those are the things you can have to see what's going on there. Okay? So in this particular case, compared with benchmark, the backtesting PCR non-stable model averaging lasso type of method improved about 15% in terms of loose mean square error of predictions. So that's not too bad. It's a simple thing, you can do that. Okay. So that's the one. The random forest with some minor modification also seems to work reasonably well in this particular case. Okay. Now this is the daily PM2.5 of one of the stations near the Kaohsiung city in Taiwan. The 10 years, so you can see that I used from 2006 to 2015, but you can update the data set, but I didn't do that. So that's roughly the product like. Okay. And the study plan like this, okay, because of strong seasonality, and you have dynamic structures. So for those in time series analysis, you can see that that's the autocorrelation function of the PM2.5. Yes, very strong seasonality. Okay. In any case, you have to model that. Hourly data are available. So to do like nowcasting example, I also included the first 6 hour data as possible regressors. So for this case, the XT involved on 48 hours, 2 days, and then the 6 hours. 48 days, 48 days, and also the 6 hours. Okay. And XT in this case called the nowcasting. It become popular in the US. Even the New York Fed actually use that to do their forecasting now. Okay. For the benchmark, I use the AIC select AR24 to do prediction. And the subsample, I use the last 2 years for the subsample type of prediction. And this is the one you have. Okay. The one on top, without this hourly means without using the 6 hours of every day. Okay. The one on above, just use the daily observation. The one below with hourly means I also use the 6 hours of every day to update my predictions. For random forest with the selection, the class 1 is hourly data. That's the first 6 hours plus leg 1 and leg 2. So only 8 of them always using the selection and so on. So this is an interesting example to look at that. Hourly observations. This is a daily average of PM2.5. Use the first 6 hours. Actually improve a lot in terms of predictions. So that's the reason the nowcasting become popular. You can see that in terms of loose mean square error, use a daily observation about 9. Use the first 6 hours, it dropped to about 6.2. Okay. And that's reasonable in many ways. Okay. So the improvement is about 28%. Is about 28%. You can think about you already use the 6 hours, so you already improve 1/4, so at least about 25%. But improvement actually more than 25%. Okay. In this particular case, because of strong correlation, the PLS and PCA all use many lag to achieve that. Okay. So now what I like to do is that you can say, well, daily average, if I know 6 hours, you already improve by 1/4. You only forecast remaining 18 hours. So I use a daily maxima. The daily maxima can happen in any time. So the first 6 hours may not contain the daily maxima. In the morning, typically PM2.5 not that big. Since the daily maxima is not quite normal, so I take a square root transform for the YT. So that's basically what I did. Oh. So basically, this is the same like that. I use the same results the last 2 years for the prediction and the same type of stuff. Still 6 hours of each stage, the first 6 hours are now casting to do that. So that's basically what you have. You can see that even for the daily maxima, use the first 6 hours, you improve the predictions. It's the first 6 hours. You still improve the predictions. Okay. So that's the reason the nowcasting, I think, it become popular, because you improve that. In this case, improvement is about 23%. Okay. Use the first 6 hours to update your prediction. For the daily maxima, improve about 23%. So that, in some sense, is quite important type of contribution. So let me, the time's running out. It seems to me, in this simple case, the simple back test seems to be doing reasonable well. So if you ask me to do that, I probably use a back testing with the nowcasting type of variable, and you can do that. The model averaging, the non-stable type of stuff seems to work reasonably well without doing any prediction about structural break. You just divide the data, divide the estimation into several categories, and so on. It pays to modify the random forest for the time series type of setup, because some variable we understand is more important than others. So that's one thing we learned from this exercise. The high frequency variable is informative. You should use that if available. The high frequency observation, it seems to be very useful. So if you like to yield forecast, we have so many people here forecast the GDP once every quarter. You may want to use a monthly observation or weekly observation to modify that. That seems to be useful. The dividend seems to be promising, but we need a more theoretical work. So those interested in derivation, econometric modeling, I think dividend is one area that seems to be promising. Okay, thank you.
So I'm very interested on your podcast for PM 2.5 in Kaohsiung.
Yeah, good.
So the regression,
yeah,
you are going to use it for prediction.
Yeah.
So how long is several hours prediction or 2 days or 2 days prediction? You know.
Basically, the one I show you is 1 day. At the end of today, I predict the tomorrow.
Okay.
That's one way to do that. The other one is at morning, 6 o'clock in the morning, I update my prediction of that day.
Okay.
So that's the two methods I show you here.
Okay.
In reality, you can predict hourly prediction or like that, but I didn't show you hourly prediction here.
So you have many models.
That's right.
And do you use what kind? Do you have a software to do that?
Yes, I show you.
What kind of software?
I use the R in my computer. R is a computer package platform. You can available. It's free to everyone.
Okay.
You can ask your assistant to do that.
and
I would like to mention here, I only focus on PM 2.5. In real prediction, there are also wind speed, humidity, okay, and wind direction are very important. Humidity is important.
Okay.
Okay, like winter time, the two reasons winter is a bad time for the PM 2.5 because the wind is from mainland, Xibei-feng. Okay. In the summer, wind is from Pacific Ocean, so we don't have to worry about that. Okay. Also, the winter time is relatively dry, so PM 2.5 had no chance to become PM 10. The PM 2.5 is the winter time is always bad. The three areas in Taiwan is bad, is Kaohsiung, Taichung area is also not good. The city of Taipei is slightly better. Okay. The only place you have a good PM 2.5 is go to Pingtung and Hualien. They have a reasonable PM 2.5 measurement. But overall, Taiwan's PM 2.5 is still relatively low compared with Shanghai, Beijing especially. Okay, we're talking about India, for example. We're talking about maximize about 100 and 110. In Beijing, 300 is almost normal. Okay. The PM 2.5, 300 to them is rather normal. Okay. But in Taiwan, I think typically we still have above the standard of 35. We still above the minimum of 35 about 50% of the time. But it's not too bad compared with some other places.
Yeah, I'm glad you point out the standard set for what is it? It's alarming.
Yeah, it's 35.
It's different.
Yeah, it's 35.
Different standard. Okay.
That's right. That's right.
And can you tell the? Okay.
You can talk to me later on.
Okay.
我注意到就是说你很多 empirical example 那个 bias，
Yeah.
都是负的。
Yes.
这个是不是有就说 systematically 有一些那个 modeling 的？
I think I think I can understand that because, for example, the benchmark, I use a mean in the forecasting sample. Okay. And in the PM 2.5 is biased because you look carefully, they're slightly downtrend in the Taiwan's PM 2.5. They're slightly downtrend. Okay, so that's the reason the prediction is something like that. Okay. Now, I have to clarify one thing. Okay. It's negative sign, but don't take that too seriously because sometimes when I do the calculation, I use a predicted value minus observed. Sometimes I use observed minus prediction. So I have to check that. Okay, because it depends on which way I do the program at that time. But that is an interesting point.
Just a simple question again. Okay. Can you combine all these things? For example, backtest.
Sure. The other way to do combine, I'm sure you take a simple average of the method I try will be better than the individual one. Yes, you can do that. Some people use, I think, Frank Debo, he tried to use a lasso type of stuff to estimate the weight of the combination. Lasso string to 0. What he tried to do is string the weight to, like if I M model, string the weight to 1 over M. He did that and seemed to reasonable. You can do the model forecast. I didn't talk about any Bayesian method to do model combination, but you can try that. That I'm sure will be better.
我有个问题，就是刚才讲这些地比较理的方法，
Yeah.
不同的东西你用最后报告的这个 learning network 不一
Yeah.
样，你用什么 criteria 去决定？还是你 try a bunch of different networks？
I try several different type of model.
How do you determine how many layers you try?
Oh, I tried that and picked the one seemed to work out the best. Now, you raise important issues because in the deep learning, you think about if I have thousands of variables, there are no reason to use all 1,000 of them. Some screening may be useful. Okay, that's an important issue to study that. Based on my experience, for example, I modify the random forest into 2 categories. That in some sense is a pre-screening type of stuff. I put one set is always there, the other set is there. So in terms of deep learning, I think you can do some pre-screening to select the more relevant type of variable, will speed up the calculation and also improve the.
But screening is only for selection of variables.
That's right.
Not about the network structure.
You can, network structure, I don't know how to select that. I suppose one thing you can do, you can come up with some type of criteria functions. But even that is still like other criteria function. You have to select a reasonable candidate to begin with.
请问大家有没有什么问题？后边。如果没有的话，我们时间也差不多正好到，然后我们是不是大家一起谢谢蔡老师跟蔡院士。
Thank you.